Good morning, everyone. I'd first like to thank the organizers for inviting me here. It's really wonderful to be back and talk to people about what they're doing. Today, I'll be talking about error correction protocols for neutral atom qubits. This is work that I started with my advisor, Shruti Puri, in collaboration with Jeff Thompson's group at Princeton. And yeah, let's get started. So there are two broad themes that I'll be addressing in my presentation today. One being that we know very well by now that physical qubits decohere. And there is, however, an error hierarchy when it comes to error correction. And this means that if you take your physical qubits and you put them in an error correcting code, depending on the dominant noise that your physical qubits experience, the correctability of those errors is different. So if your physical qubits experience dominant leakage, that's very difficult to correct. If they happen to experience Pauli noise as a dominant error, that's easier. And if they happen to experience erasures as a dominant noise, that's even easier. So given this error hierarchy, a natural question arises. What is the optimal noise channel you can engineer your qubits to experience as the dominant error? And then given this noise channel that you've engineered, what is the optimal code that you can then put these qubits into to be able to maximally correct the errors that they do experience? So that's question number one. The second question that I'll address kind of arises out of the first, in that when you put your qubits into error correction codes, certain questions which have natural and intuitive answers at the physical level, such as entangling gate fidelities, no longer have answers that are quite so clear-cut. And so it becomes useful for us to investigate and provide a performance benchmark of logical gate strategies that operate on these error correction codes and look at their fidelities, look at their overheads, look at how correctable the errors that these gates introduce are. So these are the two broad questions that I'll be addressing, but I won't be addressing them in a very general sense. I'll be addressing them in the context of the neutral atom platform. And this is a platform that has received a lot of attention recently. So as we know, neutral atoms are identical qubits, which means that you take a particular atom and you encode your qubit information in two levels of that particular atom. And then you set an array of atoms to be held in place by optical tweezers in a set of potential wells. And then you can move around these optical tweezers to have these qubits interact with each other, achieving effectively all-to-all connectivity. In recent years, there's been some exciting work showing high fidelity qubit entangling gates, both 2-qubit and 1-qubit. And even more recently, there was this nice paper from Harvard which shows a demonstration of many error correcting codes and logical operations. So in this context, let's try to answer these two questions or provide an answer to these two questions. And I'll address the first question by talking about the metastable ytterbium neutral atom and how this particular neutral atom experiences an error model that we call biased erasures, and then how we can use these biased erasures errors to achieve high thresholds for certain error correcting codes. I'll address the second question by talking about logical gate strategies for surface codes. Firstly, talking about transversal gates and how we deal with the correlated errors that arise out of these transversal gates. Then performing a lattice comparison. And then finally, kind of tying together the two topics by performing a logical gate analysis for qubits that experience primarily biased erasure errors. So, starting out. When your qubits happen to experience Pauli noise or leakage, you don't generally have an idea of something having gone wrong on your qubits. And that's generally a worse model for your qubits to experience than this newer or more beneficial error model that we call erasures. So when an erasure error happens, you get the information of exactly when and where something has gone wrong with your qubit. And a nice demonstrative example of a qubit that experiences dominant erasure errors is the dual rail. So here's an example of a dual rail qubit. Your logical subspace consists of two modes. And you have logical 0 being a photon in mode B and a vacuum in mode 1, or mode A, and a logical 1 being a photon in mode A and a vacuum in mode B. This encoding has been well known in photonics for many years, and recently it's gathered a lot of attention in circuit QED. So your logical subspace experiences the dominant error, which is photon loss. And this means that this photon that is in one of these two modes decays out of the mode, and you're left with vacuum in both cavities. And this leakage subspace is completely orthogonal to your logical subspace. And so what we can do is we can do joint parity measurements on these two modes that detects population in the leakage subspace without disturbing the logical subspace. And therefore, that allows you to detect when and where an error has occurred on your qubit. And indeed, this is the dominant error that occurs on your qubit. Another thing that I'd like to point out is that provided both of your modes behave approximately the same, the probability of 0 decaying down to the leakage subspace and 1 decaying down to the leakage subspace is about the same. And this is what allows us to differentiate regular erasures, unbiased erasures, from this new model that we call biased erasures. In biased erasures, this detectable error only happens from one state. And just extending the example that we looked at for a regular erasure, let's say we have the same logical subspace and leakage subspace, but now the dominant error is only leakage from the one subspace down to the state E, and your 0 state is not coupled at all to this E state. So when something goes wrong, i.e. you're able to detect it, it therefore becomes an erasure, you know that it's only happened from the one state. So this is a nice theoretical picture of what a biased erasure should look like. But I'll now show you how in this metastable ytterbium atom that there is leakage that is detectable, and this detectable leakage is in fact nothing but a biased erasure. So our qubit itself lives in the metastable level of this ytterbium atom, not the ground state. And this metastable level has quite a long coherence time of about 20 seconds, which means that while the qubit is idling, there's not much decay out of the logical subspace. The way we have this qubit interact with other qubits is that we excite the one state to the Rydberg level, and then have it interact with another similarly excited state to the Rydberg level, acquiring a conditional phase, and therefore enacting the control Z gate using the Rydberg blockade. It turns out that the dominant error during this entire process, the combination of idling and entangling gate, is leakage from the Rydberg level. And there's various ways this leakage happens. So you can have leakage from the Rydberg level down to the ground state. And because the ground state is orthogonal to the logical subspace, you can in fact image the ground state and detect population there without disturbing the qubit subspace. Another kind of leakage from the Rydberg level is just atomic level with a high principal quantum number, is leakage to adjacent Rydberg levels. And what we can do if this happens is that we can ionize the atom and detect population in the ionized states, again, without disturbing the logical subspace. So in effect, we've shown that a lot of this leakage that happens from the Rydberg level R is detectable. And just to simplify this picture of what's happening to our qubit, we can say that there's leakage from this state R to E, and we can pulse E and detect population there. There is, however, one more kind of decay that we have to account for in this picture, and that's decay from R back down to the qubit subspace. And this decay can take you from R to 0 or to 1, and so it causes depolarizing errors that are undetectable. They are, in fact, Pauli noise. And this kind of physical model motivates us to define a quantity that we call the erasure fraction, which is just the fraction of errors that happen to our qubit that, in fact, are detectable. And theoretically, it was proven in this paper by Wu and colleagues that you can achieve an erasure fraction of 98% in these two qubit gates. There was an experiment last year by Jeff Thompson's group where they achieved an erasure fraction of 33% by only imaging the ground state and not the excited Rydberg levels that we saw earlier. They also saw very good entangling gate fidelities, 98% for 2-qubit gates and 99.9% for 1-qubit gates. And we see that the 1-qubit gates are an order of magnitude better than the 2-qubit gates, therefore showing that our dominant error mechanism is indeed this decay during the 2-qubit gates. So this gives us a picture of how the atom behaves. Let's now look closer at the error model and understand what's happening when we detect population in the state E. If we see the atom has gone to this external state E, we know that leakage to E only happened from the Rydberg level. And we know that the Rydberg level is only coupled to the one state in the qubit subspace. And so when we detect this population in E, it's like we've measured the qubit in the Z basis with a -1 outcome. But the qubit is in fact no longer in the one state. So what we can do is we can reset the atom back to the one state, which applies this effective simple projection operator to our qubit. And if we then apply the Pauli twirling approximation to this channel, which is like sandwiching this channel with random Pauli gates, we remove the coherent parts of this error, and we get this effective noise channel. And what this means is that whenever you detect leakage or detect population in the set of external states E, what you're doing is you're applying identity with 50% probability, or you're applying Z errors with 50% probability. And so this is our biased erasure noise model. And using a similar kind of working, we can show that if you have unbiased erasures, where you have leakage that is detected from either 0 or 1, you get this kind of depolarizing noise, where you have 25% probability of I, X, Y, or Z individually. And so this establishes a difference between biased erasures and erasures. But just to clearly illustrate why biased erasures may offer an advantage over other structured noise model, I'll provide the example of a repetition code. Also, I'd like to say, please feel free to interrupt me and ask questions during the talk if something is unclear or grabs your attention. So in this repetition code, we have 3 qubits, protects against Z errors, and 2 XX checks. So if an X error did happen to occur on one of these qubits, that is in fact the logical operator of this error correction code. And so if these errors happen with probability P, we have just lost information with probability P if your errors are bit flips. If your errors are phase flips, however, when you measure the stabilizers, the XX checks on this repetition code, the XX checks next to that Z error will anti-commute with the Z error, and you'll get a defect over there. And so when you see that defect, you know that something has gone wrong, but you don't have access to the fact that the left qubit has gone wrong. You have to guess whether it was a left qubit that went wrong or these 2 qubits on the right that went wrong. So when you're trying to guess what happened, you're more likely to guess that the probability of errors is low, so it's this error that happened and not this error on the right. But in fact, if the error on the right did happen, what you'll do is you'll apply a Z correction to this qubit on the left and therefore introduce a logical operator. And so your protection to phase flip errors is P squared, but you fail to encode the logical information when you have 2 Z errors. So that's a simple Pauli picture. Let's now move over to biased erasures and reset our dominant error model. So now let's say that the left qubit experienced a biased erasure error, and we just showed that this biased erasure error is a highlight or a flag on that qubit telling you that something's gone wrong, and it's also identity or Z on that qubit with 50% probability. If identity did happen on the qubit, you've exactly recovered your code state. But if a Z error did happen, when you measure the checks, you'll get, again, the defect, the -1 stabilizer outcome appearing on that particular check. But now you have the information that it's the qubit on the left that went wrong, so you don't have to guess between the left and right outcomes. And so in order to lose your logical information in this particular case, you actually need all 3 qubits to experience errors and suffer biased erasures in order to lose the logical information. So that's the performance of biased erasure errors. Let's now reset again and imagine that the left qubit experienced a conventional erasure, which is leakage from 0 or 1 that you detect and gives rise to depolarizing noise. Now, if the noise that happened in this case happened to be I or Z, then we can detect and correct it. But if it instead happened to be the X error, then we have no information about this X error having occurred because it commutes with our XX checks. And so while we have the knowledge that something on our left qubit has gone wrong, we have no way to correct for a potential error that this unbiased erasure has introduced. And so our protection to unbiased erasure is still first order and not second or third order, as we saw with the prior error models. Though I will point out that in comparison to bit flips, we still have that flag of something having gone wrong on the left qubit, so we can do some level of post-selection, which makes the difference between those two error models. So this hopefully shows us that biased erasures offer two advantages. You have knowledge of the error location, which is not present in Pauli errors. And you also have knowledge of the error type. So you know that here, for example, it will only create Z errors. And this knowledge of error type is missing for conventional unbiased erasures. So this hopefully shows us that biased erasures offer advantages during error correction. But let's confirm this by looking at biased erasures in the surface code. And many people in the previous days have talked about surface codes, but let me do a quick recap. So here I've shown a distance 5 surface code. The darker checks are X checks. The lighter checks are Z checks. This distance 5 surface code, for example, encodes one logical qubit in the array of D cross D physical qubits. And these physical qubits can experience errors. So if a Z Pauli error happens on a qubit, then we'll see the neighboring X checks anti-commute with it and give rise to defects. If an X error happens, then we'll see the neighboring Z checks anti-commute with it and give rise to defects. It was actually studied very well in the University of Sydney that if you have bias noise, which means that if you have the probability of Z errors occurring much more than X errors, then you can use a thinner surface code because you don't have to protect against X errors to that extent. And you can get high thresholds using Clifford deformations and using the XZZX surface code. So for this particular thinner surface code, I still need 5 Z errors to create a logical operator. But because I think that X errors happen less often, I reduced my protection to X errors, and I'm saying that it's fine if I let 3 X errors lead to a logical operator. And so far, it looks like this is the noise model that biased erasures follow. It looks like biased erasures give rise to Z errors. And so we should be able to use this thinner surface code and get higher thresholds. But let's check this by looking at the circuit level noise model, where we have errors occurring after every 2-qubit gate. And this is the true physical noise model that we should look at. So looking at the circuit level operation of a Z check, we entangle ancilla with 4 adjacent qubits at its corners using CZ gates, perform erasure detection after each gate, and if leakage does occur, then we replace the atom in the 1 state and we give rise to heralded I or Z noise. So this is so far so good. But let's also now look at the X checks. For the X checks, we have to entangle our ancilla qubit with a series of CNOT gates with the adjacent physical qubits. But in our neutral atoms, we don't actually have native CNOTs. What we have, because of the Rydberg interaction, is control Z gates. And so in order to enact these control NOT gates, what we have to do is we have to conjugate our CZ gates with Hadamard's. And again, we perform erasure detection after these CZ gates. If an atom leaks, we replace it in the 1 state. And until this particular point, it's the same as the case as our ZZ check. But now we have a Hadamard gate after our replaced atom. And this Hadamard gate will change this Z error, which we saw over here, into an X error. And so after a CNOT gate, if we have leakage, we've introduced heralded X errors. And this is bad because we now have to use a bigger surface code with equal protection to X and Z errors. And we also can't see the higher thresholds, or we think we can't see the higher thresholds that we expect from bias noise. So this is a disadvantage to the surface code under biased erasure errors. But let's now further study the parameter space of errors by looking at different kinds of structured noise on the surface code. And we take a more general noise model where we say each gate suffers errors with a probability P, and the fraction RE, the erasure fraction of those errors, can be biased or unbiased erasures. The remaining errors experienced by the gates are depolarizing polynoise, and I correct these errors using a minimum weight perfect matching decoder. And the kind of plot I get looks like this. And let me just explain what I'm drawing here. So on the x-axis, I have erasure fraction. Over here, erasure fraction is 0, all polynoise. It goes up to 1 here, so all erasures. On the y-axis, I have threshold error rate. And threshold error rate, for people unfamiliar with error correction, is if your physical qubits experience errors at a rate below threshold, you can achieve exponential suppression of the logical error rate with increasing system sizes. So you want to be below threshold. As we expect, at 0 erasure fraction, our threshold is 1%. And if you're below threshold, you achieve a logical error rate suppression that goes to d by 2, approximately. So your gates, if your physical qubits experience only Pauli errors, your gates need to fail with a probability of less than 1% to achieve advantage in that regime. Now, all the way over on the right, where you have all erasures, our thresholds are 10% for biased erasures and 5% for unbiased erasures. And this is a little bit mysterious at this point because we just established that biased erasures don't preserve their bias in the surface code. But we can explain this using the concept of reduced noise entropy. So when you have biased erasures, you know that after a control Z gate, you're possibly introducing Z errors, and after a control NOT gate, you're possibly introducing X errors. But you don't have access to this information in unbiased erasures. You're introducing all kinds of errors with equal probabilities, and you can use that during error correction. And what this means is that if you have physical gates that fail even with 7% probability here, because you're below 10%, you can still scale up your surface code and achieve exponential suppression in the logical error rate with increasing system size. And another nice thing that happens with erasures is that this suppression goes as p to the d and not d by 2, as it does for Pauli errors. So you also, to some extent, win in that regard. Let's also remind ourselves that for neutral atom qubits, we're not actually operating all the way on the right of this plot. We had this theoretical erasure fraction achievable of 98%. And so we actually operate at the points highlighted by the stars, where we have a threshold of 8% for biased erasures, which is still an 8-fold improvement over if your qubits happen to experience dominant Pauli noise. So that's really nice to see. I will say, though, that we still are destroying the bias in this system using a surface code encoding. And ideally, we'd like to preserve the bias, that is, only have Z errors appearing during our circuit, and therefore achieve thin codes and high thresholds. And we do have a way to achieve that, which I won't go into detail in this talk. But this is called the hybrid fusion construction. And what it involves is adaptive fusion circuits and also some post-selection of resource states. Again, I think Shruti had talked about this last time at Koji. But the takeaway from this is that we get even higher thresholds of 18% for this construction. And we also get the ability to use thinner codes with reduced overhead at high bias. So that's really nice. So this brings me to the end of the first part of my talk, where I've explained what biased erasures are and hopefully shown you why biased erasures are good in error correction for certain codes. I'll now move on to the second part of my talk, where I talk about logical entangling gates for error correction codes. And I'll start off by just displaying this circuit. So this has Pauli gates, it has measurement and feed forward, Clifford gates, control NOTs, and also some non-Clifford gates. So this is a truly quantum circuit in some sense, and if you make this circuit big enough, it's not going to be classically simulatable. When we're enacting a logical quantum algorithm, each of these individual qubits is not going to be a physical qubit, but is going to consist of an error-correcting code or a logical qubit. And so to enact this quantum circuit, we need to understand how to do the logical gate set on these error-correcting codes. And the same way that we do physical entangling gates on our physical qubits and have performance benchmarks for them, we should be able to provide a performance benchmark for our logical gates. And this performance benchmark should be independent of when and where in the logical quantum algorithm they're being enacted. So it shouldn't matter to my performance benchmark if there's measurement, feed forward, magic state distillation immediately before or after that gate. I should be able to give you an independent performance metric for that gate. In addition to the natural benchmark of logical error rate that a given gate has, I can also provide some additional benchmarks that are the number of additional qubits, ancillary qubits I need, the number of measurement rounds I need for that gate, and also how easy is it to actually decode and correct for any errors that the gate itself will introduce. In this talk, I'll be focusing on the logical CNOT and specifically on logical CNOTs between surface codes. And the surface code in particular is nice to focus on because there's been a rich history of people studying ways to do gates on surface codes. So a well-known approach that is established for fixed qubits that you can't move around between each other, is lattice surgery. So you have your static surface code patches, and you have some bridging region of ancillar qubits in between them, and you start measuring stabilizers in this region to connect the logical operators of the two surface codes and perform joint Pauli measurements on them, therefore enacting, in some sense, measurement-based operations. The second method for doing logical gates and surface codes is braiding. So in braiding, you have a large patch of surface codes and the relevant stabilizers, but then you stop measuring some stabilizers in a small region, therefore poking a hole in your surface code. And in kind of a similar way to we talked about yesterday, braiding anions around each other, you can braid these patches around each other, and each of these patches encodes one logical qubit, and therefore you perform operations on these logically encoded qubits. A third way that perhaps is more intuitive is transversal gates. So if you want to perform a 2-qubit logical transversal gate, you take two surface codes, move them on top of or next to each other, and perform physical entangling gates between each pair of corresponding qubits in your two surface codes. And this is perhaps the most intuitive strategy to use if you have qubits that are in fact movable. And so in today's talk, I will start off by focusing on transversal gates and then do a brief comparison with lattice surgery. But I'll first kind of orient to the language that I'll be using to describe these strategies. I'll be looking at the kind of space-time decoding volume for the two surface codes involved in the logical gate. So up on the left, you see the two surface codes, and in the bottom right is the space-time decoding volume. So you can imagine that I've put the surface code at the base of this cube, and then I've measured it for d rounds in time. Time is going vertically upwards. And in this process, I collect information about errors happening on the data qubits or happening during the measurements. So for example, let's say that at some point inside this space-time volume, a z error happened on one of my qubits. When I measure the stabilizers, that z error will give rise to defects. And then I can apply a decoder, such as a minimum weight perfect matching decoder, that finds the most probable edge that could have given rise to these defects. And crucially, this will come back later, this edge must have at most two endpoints. So here it's natural to say that, oh, I can just connect these two defects along this edge, and that edge corresponds to the data qubit z error. And therefore, that is the correction that my decoder proposes for this problem. So this is the language I'll be using for this transversal CNOT study. But now let's go and discuss the transversal CNOT itself. So let's say that I've taken my two surface codes. I've measured them for a certain number of stabilizer rounds. I then enact the logical transversal CNOT by moving one surface code over the other and performing physical entangling gates between each pair of corresponding physical qubits. I can then move them back apart, and then I continue measuring stabilizers on my two individual surface codes. So let's look at how errors propagate during this process. Let's say at around k, before my logical CNOT, there was a z error on my target surface code. This is the control surface code, this is the target surface code, the decoding space-time volumes. So when I measure the stabilizers at that round k, I see defects appearing on my target decoding volume. Nothing happens for a while as I continue measuring my stabilizers, but then I come to the round where I'm enacting the logical CNOT. And what this logical CNOT does is it takes this z error on the target surface code and it copies it over to the control. So when I measure my stabilizers at this round immediately after the logical CNOT, I suddenly see defects appearing there as a result of this propagated error. And so what this process means is I've only had one truly random error happening throughout time in this particular example, and that random error is this z error at time k. All other defect patterns are arising out of propagations of this error. And so if I try to draw an edge between the defects that arise out of this error, I can't draw a simple edge. I have to draw a hyperedge that connects 4 defects, all of which have arisen out of this single error. And why this is bad, I'll just briefly address in a moment. But let me also note is that because of measurement errors, the pattern of defects I see arising out of this propagated error can also be deformed up and down in time. So a measurement error can take those defects, move them to a later stabilizer round, and so I have a more complex pattern of defects along my hyperedge. And so it becomes useful for me to look at a few rounds of measurements before and after my logical CNOT in order to identify defect patterns that have arisen out of measurement errors. So I have my hyperedge, and I need to figure out what error gave rise to this hyperedge, which means that I need to use some kind of hyperedge decoder. Now, when we have simple edges that connect up to 2 defects, we can use minimum weight perfect matching. But if you have hyperedges that connect 4 defects, like I showed on the previous slide, that problem is in fact NP hard. Finding the most probable error takes exponential time to decode and figure out. And this is not desirable for us. And luckily, there's been an algorithm developed by Nicola Delfos, which is a generalization of the union find decoder to LDPC codes and hypergraph. And we call this the HUF algorithm. And my colleague Yue from Yale has also developed a nice open source implementation of this HUF algorithm. So what HUF does is that it doesn't try to find the truly globally most probable error that gave rise to a pattern of defects along hyperedges. It finds a local optimum, or like a reasonable approximation of what it thinks is the most likely error. And it is able to do this in polynomial time, which is good. But the drawbacks of this algorithm are that as the complexity of the hypergraph increases, it performs worse and worse because the reasonable approximation it tries to find becomes less and less close to the truly maximally accurate solution. And additionally, because it's trying to solve a quite complicated problem, it's quite slow at reasonable error rates compared to a matching decoder. So let's look at the performance of this HUF algorithm on 2 kind of example experiments. One is a memory experiment on 2 surface codes. So here I've shown the decoupled decoding volume of surface code 1 and surface code 2. And then I compared the performance of the HUF decoder on this system with a system where I've done a logical CNOT between my 2 surface codes. And the way I'll perform the comparison is I'll look at this kind of parameter space. Okay. So in this parameter space, on the x-axis, I'm plotting the threshold error rate. And the y-axis, I'm plotting the logical error rate given a set of physical parameters. So we see for the memory experiment, HUF has a threshold of about 0.9%. This drops to 0.76% for the logical CNOT because the HUF is trying to solve a more complicated problem. This isn't such a big drop in the grand scheme of things, perhaps. But what is maybe more detrimental is the fact that our logical error rate is increasing by more than 3 times when we apply the HUF algorithm to one experiment versus the other. And this is undesirable because we're really only doing 1 extra layer of entangling gates on our system compared to the memory experiment, this logical CNOT entangling gate. And so we'd like to not see that drop. There's also been a recent work that came out. Oh, yeah, sure. There's also the memory decoder that I can place on this landscape, which is decoded using minimum weight perfect matching. And we also see a threshold of 1% and a slightly higher logical error rate because matching cannot deal with hyperedges that come out of Y errors. There's also been some recent work that looks at decoding hypergraphs using a modification of the HUF algorithm where you add belief propagation to your decoding graphs, and then you perform hypergraph union find. And this particular paper looks at 2 circuits. It looks at many more circuits, but I will focus on 2 particular circuits. One is a logical CNOT, where they choose to isolate the logical CNOT by using D rounds of measurements before and after the CNOT. And the second is a depth 32 logical circuit, which involves 32 layers of logical gates, but they're only separated by one round of measurement after each gate. And on this kind of parameter space, these two experiments look like this. So for the single logical CNOT, we see a threshold that's pretty much maintained at 0.95% and a certain logical error rate. But now, because in the second circuit, the hypergraph union find decoder is solving a much more complicated problem and is not able to fully uncorrelate the gates between measurement rounds, the threshold drops and the logical error rate increases for this particular circuit. And additionally, what this means is that that particular circuit does not provide a true benchmark of the performance of an individual logical gate because we're not able to uncorrelate the errors between measurement rounds. And so we'd like to be able to provide a method of decoding logical gates that maintains the performance. That means that we're somewhere in this regime, and also is able to fully parameterize the performance of one logical gate by itself. Just to complete this picture, let me also introduce the original proposal of how to decode CNOT gates, which was given over 2 decades ago by Dennis. And that has a threshold that's half that of matching and also a pretty high logical error rate. So we're seeing that we're already starting to see many improvements over that original proposal. So our strategy to achieve a maintained performance compared to memory of a logical CNOT is called ordered decoding. And during my analysis of how ordered decoding works, I'll focus on Z errors, though you can easily extend the analysis to X errors. And we'll use the simple fact that Z errors propagate from the target over to the control. And let's say I perform a logical CNOT experiment, and I see the following set of defects in my 2 decoding graphs, control decoding graph and target decoding graph. I'll now use my ordered decoding strategy to figure out how to successfully correct this particular error pattern as an example. So in ordered decoding, what I do is I first choose to only decode the target. And I do this because I know that these Z errors only propagate from the target over to the control. So I ignore the control, and I look at potential solutions that, let's say, a matching decoder would come up for this particular error pattern. So it might think that a lot of measurement errors happen that connected these 4 defects along vertical strings, or it might think that fewer data qubit errors that happened and connected these defects along horizontal error strings. And this horizontal kind of matching seems more likely than a matching that involves lots of errors. So my decoder is going to decide that this is the solution that it thinks should be used for this particular set of defects. And now we fix this solution, and we use the fact that errors on the target that happened before the logical CNOT will now propagate over to the control on the logical CNOT round and give rise to heralded defects. So we know that this particular Z error will go over to my target, create those 2 defects, and a Z error that's been propagated over. So I can pre-account for those propagated defects, remove them from my consideration, and then decode the remainder of my control decoding volume separately. So this is the procedure that I'm going to use. And when I use this procedure and I build up a threshold plot, it looks like this. And again, on the x-axis, what we're looking at is the physical error rate. Y-axis is logical error rate given a range of system sizes. And we see that the different system sizes intersect at the threshold error rate of 1%. So I can use the data I get from this plot to go back to the parameter space that I was exploring a few slides ago. And I place this point on my parameter space. There's a lot of points now. But we can just focus on this area. So my memory experiment is the orange diamond with matching. The blue square is my ordered strategy using a matching decoder on a logical CNOT. The key things to take away are that we've maintained the threshold exactly, and we've caused a slight jump in error rate, which we understand why it happens, and we can also prove that the slight jump will go asymptotically to 0 at very, very low physical error rates. And a nice thing about this ordered strategy is that if I want to optimize for this given set of physical parameters, Maybe I think that, oh, this HUF decoder does very well for memory. I want to use this decoder for this set of physical parameters. I could use an HUF plus order decoding strategy to get a point right here and therefore achieve a lower logical error rate even for my logical CNOT in this particular parameter regime. So our order strategy is quite general and can be applied to different decoders as well. So that brings me to the conclusion of my discussion of dealing with correlated errors in transversal gates. That's one approach to do a logical CNOT on surface codes. Let's now move on to a quick comparison with lattice surgery. So as a brief recap, when you want to do computation with lattice surgery, you should do projective Pauli measurements. For example, you have two surface codes and some uninitialized ancilla qubits between them. In order to do an XX measurement, you start measuring stabilizers in this region, and the product of X stabilizers here gives you the XX measurement outcome. However, there may be measurement errors during this process, and so in order to be fault tolerant to these measurement errors, you need to perform this about D times. When we want to perform a logical CNOT using the same process, we can decompose the logical CNOT into such joint Pauli measurements. And the circuit to do so looks like this. So you take your control logical qubit and entangle it with an ancilla logical surface code patch using ZZ measurements. And then you take your ancilla and entangle it with the target using the same XX measurement that we just saw. And you measure out your ancilla and you apply Pauli updates. So it looks simple enough. And using a direct comparison with memory, we can say that this ZZ measurement takes D rounds, this XX measurement takes D rounds, and so my entire logical CNOT enacted using lattice surgery takes 2D rounds. And in fact, my decoding problem looks very similar to that of memory and has been studied quite well in this paper by Chamberlain that came out a couple of years ago. And so when we take this system and we add in its fidelity and threshold back into our performance landscape that we were looking at earlier, we get the following blue point. So we get the same threshold because it's basically an extended memory decoding problem, and we get a jump in logical error rate because we're using like this extra ancilla logical qubit, and there's just much more space for errors to occur in this system. So this tells us, this gives us a nice picture of what decoding strategies can look like. But until now, we've just studied a single control, single target kind of experiment. A neat thing about lattice surgery enacted CNOTs is that you can do single control, multiple target CNOTs using the same number of measurement rounds. So if I want to do control target, all I have to do is extend my XX measurement to these multiple targets. And it turns out this same kind of intuition can be applied to transversal gates. So I can also do this control target using back-to-back control NOTs in a transversal scheme without violating the conditions or the requirements of my ordered decoding, needing to decode target first and then control, because I can still decode my target and then use that information to update my control. But if there was control target here, then I would need to like separate them and isolate them in order to identify the corrections. So for both my logical CNOT schemes, I have now identified ways to perform gates efficiently. And now we can extend this analysis to CNOTs that are used in general circuits with the two kind of requirements that we've established. That if I have single control multiple target gates, I can do them back to back or at the same time. But I do need about D rounds between gates that conflict in their requirements of control and target. And what this does is that it allows me to exactly benchmark the performance of a logical gate, given that I know how a decoder performs on a memory experiment of the same surface code size and physical error rate. And so the results I get look like this. And I'll go through the rows one by one. So for a transversal strategy, my logical error rate gets slightly magnified compared to the memory error rate, dependent on the number of targets. For lattice surgery, I see a bigger magnification, though compared to a memory experiment, we see some kind of inverse suppression at single control, many target gates. So, and for both processes, the decodability is equivalent to memory because we reduce down the decoding to nothing but a simple matching problem that doesn't involve hyperedges. For performance metric of number of ancillary qubits, my transversal gate doesn't need any additional qubits because I'm just taking the two surface codes and moving them on top of each other. But my lattice surgery approach does need extra qubits because I need the qubits in the bridging region in order to perform the projective Pauli measurements. Also, for the transversal gates, I need about d rounds per entangling gate in order to isolate the gate and decode it completely. But for lattice surgery, as I just showed, you need d rounds for the XX measurement and d rounds for the ZZ measurement, so you need 2d measurement rounds per entangling gate. So what this tells us is that if you have movable qubits, there is, at face value, a transversal gate advantage. And perhaps that is the strategy that we should move forward with at this point in time. So this is a picture of what logical CNOTs might look like in general circuits. But until now, I restricted my analysis to Pauli noise. And now I'll go back and connect this analysis with the first part of my talk, where I addressed biased erasure qubits. And let us remind ourselves that biased erasures tell us both where the error happened, so you get a flag on that particular qubit, and also tells you the error type, so you know whether it's X or Z. And again, we're using the error model where gates can experience errors, out of which an erasure fraction RE are now biased erasures, and the remainder are Pauli errors. And I'll bring back the same graph that I showed earlier in the presentation, where I'm now plotting the surface code memory experiment with a matching decoder in this noise model. And if you recall, we see this threshold error rate of 1% at 0 erasure fraction, going all the way up to 10% at 100% erasure fraction. Because our lattice surgery decoding scheme is exactly the same as memory up to time boundaries, we get the same curve for a lattice surgery CNOT, although I will say that this graph is not able to capture the kind of multiplication in logical error rate that we see for a lattice surgery scheme. Now, when we introduce the transversal CNOT to this biased erasure qubit scheme, we see the following graph, where at low erasure fractions, 0 erasures, like 20% erasures, 40%, we see that our transversal CNOT exactly has the same performance as a memory or lattice surgery scheme, though at very high erasure fractions, we see a slight drop in the threshold from like 10% to 8% for a transversal CNOT. And this drop can be attributed to weight 0 loops in the decoding graph around the logical CNOT. So our decoder is not able to successfully determine if these two defects appear, and there are many weight 0 edges between them, which is what will happen when you have high erasure fractions and erasures cause weight 0 edges. It's not able to determine which of these paths really caused the erasure or really created the defects, and that confuses its information about which error it should then send on to the control and use for decoding. But despite this, what we can take away from this graph is that this biased erasure advantage, where we see high thresholds for biased erasure qubits, was evident in the memory graph, but is still maintained for the transversal CNOT graph and the lattice surgery graph. So our biased erasure advantage is still maintained for logical operations. And that brings me to the conclusion of my talk. I told you about this really nice structured noise model that we call biased erasures. And I also introduced an efficient decoder for a transversal CNOT that has no higher complexity than matching, let's say, but also preserves the thresholds and up to some constants, the error rates of a memory experiment. And then we've used this approach to study different logical gate strategies in order to find the resource overhead that we use for each entangling strategy. There are some interesting directions that we can take this analysis. We can do further, more like detailed analysis of the errors that actually occur during entangling gates. For example, when we move atoms around, there's some enhancement of the atomic loss rates from the tweezers because of the movement itself. There's also the fact that until now, our CNOT doesn't really account for the overhead that our logical quantum circuit will need if you use non-Clifford gates. So we can also benchmark these non-Clifford gates in the same way. And ultimately, we hope that our analysis will help find a resource-efficient manner of conducting fault-tolerant quantum computation. Thank you.
Any questions?
Yeah, I have a question to the last part of the talk. noise on the surface mode, and then you have a plot with this threshold error rate and like the biased and the unbiased.
Right.
Why is can you repeat what the definition of your threshold error rate is? Because the biased was like higher than the non-biased.
Right.
I'm confused about that.
Okay, so I think there are two parts to the question. What is the definition of a threshold error rate? So for that, let me go to this plot. So this is a threshold error rate plot for an operation. So when I look at a threshold error rate, I plot physical error rate versus logical error rate for a range of system sizes. And there's one physical error rate. Here it's 1%. And if I'm below 1%, then as I increase my system size, my logical error rate gets better and better. So that's what a threshold error rate means. And when I build my quantum system, I would like my physical entangling gates to be below this threshold, because that means that I get better the bigger I make my system. So that's what threshold error rate in itself means. But to come to your answer of like why we see this difference of unbiased erasures and biased erasures, it's because of the amount of information we have about the errors that happen for the two cases. So for unbiased erasures, we don't know whether I, X, Y, or Z happened. And we can't use that information while decoding because we don't have access to it. But for biased erasures, if I have a control NOT gate, that control NOT gate could only, on the target, introduce I or X. And the control Z gate could introduce I or Z on both qubits that are involved in. And I can, in fact, use that information when decoding to adjust, if you want to talk about it in decoder language, to adjust the edge weights in my decoding graph, or just to like optimally connect the defects along those particular error mechanisms. And so because I have more information to use during decoding, my thresholds improve compared to in biased erasures compared to unbiased erasures.
So higher threshold is better.
Yes, higher threshold is better. So like I think like a nice example to use is that if I have 7% error rates here, then I'm below threshold here, which means I still see exponential suppression if my model was biased erasures. But if my error model was unbiased erasures, then I'm above threshold. And in fact, I don't see any advantage to scaling up, but at those high error rates, I'm so far above threshold that it's 50% failure probability probably. Yeah.
Georgia.
Okay, Kaavya, I just wanted to ask about this Pauli's world that you get.
Right.
So you mentioned when you have a qubit in the Rydberg state, there's many different ways you can have erasure to another Rydberg state or decoding back to the ground state. And then you have this pulse and you return it to the qubit subspace and you generate this Pauli world.
Right.
I was wondering, do you not have to be quite careful about measuring exactly what type of erasure you have in order to generate this specific pulse to do this in all different cases? Or, yeah.
No, that's a really good point. And so that is exactly why in this experiment by Jeff Thompson's group, they only image the ground state, because there's different ways you can leak from the Rydberg level. And imaging and detecting the leakage to the ground state is much easier than imaging and detecting like the different Rydberg levels. So imaging one is easier than the other, but it doesn't really affect the Pauli twirl that you do to both kinds of errors, because both kinds of errors are like leakage to disjoint spaces.
Okay, so for all, okay, so if you had another leakage to a Rydberg state, would you apply the same pulse?
Yes, so okay, wait, which way is that? Yep. So what they do during this process to be like very specific is that they enact the Rydberg gate. The Rydberg gate is supposed to be enacted, and the qubit is supposed to come back down to the one level. And then what they do is that they apply like a big pulse to many neighboring Rydberg levels, which also catches leftover population in that Rydberg level, but also like the nearby Rydberg levels. And they excite that whole bunch of populations up to this ionized state. Does that kind of address what you were asking?
Okay. Yeah.
Thanks very much. Excuse me. Thanks very much. I was very interested in the kind of logical gate benchmarking you were doing, but I've gotten fixated on perhaps a side issue. So with this the hypergraph union find,
Right.
when you apply that just to a memory error, you find at some error rate that you're looking at, like greatly reduced logical errors relative to the minimum weight perfect matching.
Yes.
Even though the threshold is lower.
Yes.
I suppose, I'm wondering if you have, I mean, it might be desirable at some operating point to use such a code in preference to one with a higher threshold.
Exactly.
And there's a much bigger difference than I would have expected. I'm just wondering if you have any sense there of why that's occurring.
We do have a sense there. Let me see if I still have that slide. Right. So Y errors can happen on our surface codes, and Y errors give rise to 4 defects. So when we do matching, what we have to do is we have to break down Y errors into like X errors and Z errors and decode them separately on 2 graphs. But if you do a hypergraph decoder on that, it doesn't have to break it down, and therefore it's like more intuitively almost able to deal with Y errors. And so that's why we see that drop in logical error rate for hypergraph union find over matching.
And is there any hope of reproducing that kind of behavior in something that actually runs faster than faster than matching?
So,
I mean, hypergraph, I really don't want to slow the decoder as this works.
Yes, I believe so. So I think there's a really nice paper by Oscar Higgett, I believe, where they apply belief propagation between the 2 decoding graphs to kind of like, oh, if there's 2 defects here, it's more likely that there was a Y error here, so you update the probabilities here, and then you decode using matching. And they call that belief matching. So that's a nice way, and they do see improved ability to deal with Y errors there.
Any other questions? No.
Can I ask about your decoder? So is it possible to understand it as a projection decoder, where you use the result of the first decoding problem to like change the edge weights on the second one?
We don't change the edge weights per se. We just update our information about the defects. So there's, let me go back to that slide. So when I have this collection of defects, I decode this completely. I then realize that this will propagate here, and I kind of remove these defects because I know what created them. And then I just simply decode this. I imagine there might be some advantage to doing some reweighting, but we haven't studied that.
I guess you could understand that as reweighting the edges to just make them like have to match.
So that's a very good question. I did try that. I did try that in the context of erasures. I think for polynoise, it will do exactly what you're suggesting. But when you introduce erasures back into it, there's some confusion that's introduced to the decoder that maybe we could talk about later.
Any other questions? Actually, I have one. On your last slide, you mentioned modeling the erasure exacerbation due to moving the array. What's like the error model there? Is the erasure proportional to how far I move it, or is it just like a static handoff?
That's a very good question. So I think I'm not an expert in this, but I believe there's 2 ways to model the atom loss due to movement. One depends on the acceleration that your atoms go through in the optical tweezers, and one is like dependent on the speed and distance kind of combination. So it does linearly depend on the, or not linearly, but it is a function of the amount you have to move these surface codes. It's not a constant.
Oh yeah.
Just on the final slide, you mentioned sort of not with operators. I was wondering how you affect this sort of uncomplicated erasure errors.
So if I'm correct, you're asking about how erasure errors will complicate our non-Clifford benchmarking.
Well, I guess the other way around, but both ways.
I don't think it will necessarily complicate, erasure errors will introduce additional complications to that particular problem. I think the interesting part of benchmarking non-Clifford gates is that there are so many procedures that people have come up with of introducing these magic states into surface codes that just like figuring out the methods that each of them, like each of the particular methods that everyone has proposed, and figuring out what's like the optimal method is going to be a difficult parameter space to go through. But I don't think there's going to be any additional effects from erasures during that process, because erasure is just detecting like leakage outside the subspace.
I guess maybe to sort of come in a little bit, here you rely on the fact that it's an erasure error, and you know that it's like let's say biased-erasure error or something error, and you know the location as well. But then when these sort of errors are propagating through like Clifford gates and propagating through non-Clifford gates.
I begin to see what you mean. So you're right in the sense that we have here kind of relied on perfect erasure detection. So we've here relied on the fact that after every gate, I can immediately apply that detection pulse, and I can figure out that qubit has leaked. But I think the problem you're referring to after like non-Clifford gates will be exacerbated if you can't do this reliably. Like if your pulse does not pick up the erasure happening, the leakage happening, or you can't do the pulse after every gate. I think that will become a big problem in that regime.